Remember, we arrived at the Einstein action and the Einstein equations. So the Einstein action is this expression here. So the overall action, in encoding everything we know about physics, depends on the metric and depends on all kinds of matter fields, matter and radiation fields, psi. And it starts out like this. There is a term called the Einstein-Hilbert action, which has the Ricci scalar, which depends on the metric, this prefactor, and then the Lagrangian of the standard model, the Lagrangian of all the physical fields that we know of. And that Lagrangian depends itself on the metric, of course, because there will be some covariant differentiations and contractions of indices going on. And it depends on all of the fields and possibly on their covariant derivatives. But only the first covariant derivative. So that's the overall action. And then if we want to know what the classical equations of motion of the matter fields are, we just have to functionally differentiate the total action with respect to the matter field in question that we are interested in, set that equal to 0, and that gives us the equation of motion for the matter field. Oh, by the way, one example of a matter field would be electromagnetism, which of course is normally thought of as radiation, where this term would be minus 1 over 16 f mu nu f mu nu. And you see that there are upper and lower indices, which means the metric is in there. Electromagnetism knows about the metric. It's affected by curvature. Okay, so we get a bunch of equations of motion, such as the Cairngorn equation, the Dirac equation, and so on, from differentiating the action with respect to the matter fields, where this term never contributes. Also, I dropped the cosmological constant term for now, just because it wouldn't have fit on the equation here, on the line here. Then, if we vary the action with respect to the metric and set that equal to 0, then we obtain the equations of motion for the metric. And that's the Einstein equation. The metric occurs in here, and the metric occurs in there as well. So we get two sources. So we have two sources of terms when we functionally differentiate the action with respect to the metric. If we differentiate this Einstein-Hilbert term, then we obtain this for the derivative. If we differentiate the matter action with respect to the metric, then we obtain the energy momentum tensor. And so overall, this equation, after some extensive calculations, becomes that Euler-Lagrange equation, the Einstein equation, which deeply relates energy and momentum to the curvature of space and time. Now, normally it is read from right to left. You have matter fields, and they imply some energy and momentum. So we have an energy momentum tensor, and that is then curving space. But as has long been pointed out, you could also read it from left to right. You could always take any arbitrary metric and make it a solution of the Einstein equations by saying, okay, you cook up some arbitrary metric, calculate then what the Ricci scalar is, what the Ricci tensor is, calculate therefore the left-hand side, and from that you get a right-hand side, which is some energy momentum tensor. So for every metric, there is some energy momentum tensor that will solve the Einstein equation. Of course, that energy momentum tensor may not arise at all from any known physical fields under any circumstances. So the difficult part is really going from right to left, having physical fields in reasonable circumstances producing energy momentum tensor and then calculating the curvature. Overall, we have to solve all of those equations, of course, at the same time. The equations of motion for the particles, which have the metric in them, and the equation for the metric, which has the particles in them, so the energy momentum tensor. And you can see how this is a very complicated, highly nonlinear business, because especially the metric occurs in all sorts of non-trivial ways. It occurs directly in here, but the metric is also in here and in there with its derivative, and it's also on the right-hand side. So the metric is everywhere in there, but in a highly nonlinear way, and that makes it so difficult to solve the Einstein equation at the same time as the matter equations of motion. Now, this is the traditional way of writing the Einstein action and the Einstein equation. Now, we can do better. Let us allow ourselves now, after all this preparation in this course, to use arbitrary bases in the tangent space. In particular, orthonormal bases. Remember how that works. So our aim now is going to be to re-express this, the action and the Einstein equation, in terms of tensor value differential forms, where we make use of the arbitrariness, the freedom to choose the bases in the tangent spaces, whichever way we want. In particular, we can choose the bases such that the metric is always eta mu nu, right? So let's do that and see how the Einstein equation and the Einstein action look in that case. And then in the next lecture, we will use that formalism and solve the Einstein equation for FRW or Friedmann-Lemaitre spacetimes. Okay, so how did that work? The use of frames. So we choose in the tangent and cotangent space of every point of the manifold a basis. A basis E mu of vectors in the tangent space, a basis theta mu of vectors in the cotangent space, and we choose them dual bases, right? So that theta mu evaluated on E nu is Kronecker delta. That makes the two bases dual to each other. Canonically, when one first studies general relativity, the choice is usually made for us, and we just choose for the E mu, the d by dx mu, and for the theta mu, the dx mu. So we choose these bases, but there is no reason to choose them. And in particular, there's no reason to change the bases in the tangent and cotangent spaces when we change coordinate system. The two things have nothing to do with another a priori. You see, if we do choose our basis in the tangent space always along with the coordinate system, so we have one tangent vector or tangent vector field, then in one coordinate system, it has this form with these coefficient functions. These are the basis vectors. And then if we go to another coordinate system and then we choose these basis vectors, then the same vector has, of course, different coefficient functions. And of course, that's usually how the differential geometry is introduced for general relativity. But you see, these coefficient functions change from one coordinate system to another only because we chose to use this basis in the tangent space in one coordinate system and that basis if we choose the other coordinate system. If we stick to the same basis, the coefficients are not going to change. For example, in the second coordinate system, we may still want to use this basis. If we do, the coefficient functions don't change. So in general, we can choose an arbitrary basis in the tangent spaces, and then a given vector field will have certain coefficient functions, which are scalar functions, coefficient functions times those basis vectors, and as you change coordinate system, nothing changes. That equation just stays the same. Right? Same basis vectors, same coefficients, same vector, same tangent vector. Remember that it's just like in any vector space. A vector is a vector. It doesn't change when you change bases. The coefficients in which it is represented, which are used to represent it in terms of a basis, may change, but the vector itself stays the same, of course. So if you don't change bases, you don't change coefficients either. And conversely, even when we stick to one coordinate system, we are still free to change the basis in the tangent space. So for example, we could choose the theta mu vectors for the cotangent, the basis in the cotangent space, and then even without changing coordinates, because coordinates really have nothing to do with it, we can at any time choose to use another basis in the cotangent space. So the basis of the theta mu primes. It's just another bunch of basis vectors in the cotangent spaces. And we have this matrix that maps the old basis vectors into the new basis vectors. And we do that at every point. So the thetas are dependent on x, the theta primes are dependent on x, and this change of basis matrix depends on x. So at some points in the manifold, you may want to choose the same basis, and some other points of the manifold, you may want to choose another basis. This is a position-dependent change of basis. And the dual basis of the tangent vectors has to transform in this way so that the duality is maintained. So that when theta evaluates on E, you get Kronecker delta, and when you evaluate a theta prime on an E prime, you also get a Kronecker delta. So that automatically tells us that the transformation rule, the change of basis in the dual basis has to be like that. So for example, let's take a tangent vector expanded in the first basis. Well, then we can also, because E is A times E prime, we can also write it in this way. And then you see that the same tangent vector has these coefficient functions with respect to the E basis, and it has these coefficient functions with respect to the E prime basis. So these coefficient functions are the psi prime. So we have that the coefficients of a tangent vector or of the tangent vector in the new basis, the new tangent space, are given by A nu mu, psi mu, where these are the old coefficients of the same tangent vector. And no change of coordinate system, just a change of basis in the tangent space. Not only tangent vectors transform this way, similarly you can show that also the curvature 2 form transforms the same way. The curvature 2 form, remember, it's really the curvature tensor where two of its indices, which were antisymmetric, the last 2 indices, were interpreted as a differential form, and the remaining 2 indices are one upper, one lower. So here's the curvature 2 form, and it has an upper, it has a lower index. And if you don't change bases in your tangent or tensor spaces, then these coefficient functions are fixed, even if you change coordinate system. If, however, you do choose to change your basis in the tangent and tensor spaces, then this is how the coefficient functions transform, just the same way that a tangent vector would, with an A for the contravariant indices, the A, and with an A inverse for the covariant indices. As usual, the connection 1 form, the affine connection, is not transforming tensorially. If you look at the connection 1 form, remember that's really just a Christoffel symbol where one of the lower indices was identified with the 1 form. Yes? Yeah,
so just a question. So these transformations, they can be any linear transformations, or they have to be the Poincare group?
No, so far they're just arbitrary. Yes, yes. Completely arbitrary. We have not specified that the E are orthonormal. We are not specifying that orthonormality should be preserved. Just any basis. Okay, so here we have the affine connection 1 form, which is just this in terms of the Christoffel symbol, and it doesn't transform tensorially. We know that already. Instead, it transforms almost tensorially. You see, it has an upper and a lower index, so it should transform with an A and an A inverse if it were tensorial, but there is this extra term here, and we know that term already from the special case where the change of basis is induced by a change of coordinate system when we choose to stick with the basis that comes with the coordinate system, with the dx mu. But this is much more general. This is the transformation law for any change of basis in the tensor spaces, whether motivated by a change of coordinate system or not. So now, but this is all nice to say, but how do we actually work with that? How do we actually put numbers and concrete objects to this? Okay, so in an arbitrary coordinate system, see, in practice, we want to work in a coordinate system. Of course, whatever we do should not depend on it. So we choose a coordinate system, and along with the coordinate system, we know that we have these basis vectors in a cotangent space. But they may not be the most convenient to work with. So we allow ourselves the freedom to work with other bases in the cotangent space. And any other basis in the cotangent space has to be obtainable by a linear map from that basis. So whichever basis in the cotangent space we want to work with, this is how we can express it. So our choice of bases in the cotangent space will be encoded by such a matrix Aij of X. There are other ways to specify bases in the cotangent space. For example, you could take 4 independent scalar functions and look at their differentials. So we have 4 scalar functions, f1, f2, f3, f4. And then we look at df1, df2, df3, df4, their cotangent vector fields, and generically, if you choose generic functions, the cotangent vector fields that you obtain by taking the df are going to be linearly independent. So that's another way of doing it, but that wouldn't be convenient. It's much more convenient to do it that way. Of course, if you change coordinate system and you want to express still the same choice of bases in the cotangent space, well, with different coordinates, you get different x tildes j now, and so you need a different transformation matrix to get to the same basis vectors there. Now, let's be more picky and choose convenient bases in the tangent and cotangent vector space, namely orthonormal frames or tetrads. We say that the frame consisting of a basis, of a dual basis, a set of dual bases in the cotangent and the tangent space is orthonormal if at all points of the manifold it is true that E mu, E nu is eta mu nu. So if they are orthonormal with respect to the metric. Notice that there is no notion of orthonormality between E and theta. They are dual to each other, and to choose that theta evaluates on E as the Kronecker delta has nothing to do with orthonormalization. It's just a choice of dual bases. Only vectors that live in the same space can be orthogonal to each other, or non-orthogonal to each other. And the E's live in the same space. But the E's and the thetas don't live in the same space. They don't have a notion of orthogonality. So the vectors, the tangent vectors E mu and E nu are said to be orthonormal if their contraction with the metric is, well, in the Riemannian case, we would want it to be the Kronecker delta, but in the case of relativity, we need to have this minus sign here for time. So the orthonormality is given by this condition here. And in this case, we can write the metric then as minus theta mu, theta 0 plus sum I equal 1 to 3, theta I tensor theta I. Right? This is just expressing this matrix in terms of that basis. So you see, if we choose the thetas and the E's orthonormal, in particular if we choose the thetas orthonormal, and you can do that exactly the same way with the metric, it's just that you have, in this case, you have the metric with lower indices. With the thetas, you would have to use the metric with the upper indices. If you choose them orthonormal, then the metric becomes that matrix everywhere on the manifold. you may wonder, how do we know that exists? How do we know that at every point of space-time there is a choice of basis vectors such that the metric takes this form? Now you know that the metric, when you change coordinate system, transforms with the matrix to the left and the matrix to the right. And you may think that this is like diagonalizing an operator in quantum mechanics. It is not. It is not, because the structure is different. We have two lower indices with the metric. And that means that they transform with the same matrix. That's not like diagonalizing in a Hilbert space, a function. So we are not applying here any spectral theorem. It's a different reason why the metric can be always diagonalized and put into this exact form. So why is it that we know that it can be put always in that form? Well, remember that at every point in the manifold, we can construct such an orthonormal basis in the following way. At every point in the manifold, remember, we can define a Riemann normal coordinate system around that point. For every point in the manifold, we can choose to be the origin of a suitable Riemann normal coordinate system. Right? With a tangent map, you take the with the exponential map, which takes tangent vectors into points in the neighborhood. And if we choose the a Riemann normal coordinate system around the point P, then remember we showed that at the origin of a Riemann normal coordinate system, the metric tensor G mu nu actually is eta mu nu. At the origin of a Riemann normal coordinate system, it takes the coefficients are eta mu nu. Which is to say that the dx mu at the origin of a Riemann normal coordinate system, if the x mu belong to the Riemann normal coordinate system, if this is the coordinate system of a Riemann normal coordinate system, then these dx mu are an orthonormal basis. Of course, at any other point than the origin of the Riemann normal coordinate system, they have no reason to be orthonormal. But at the origin of a Riemann normal coordinate system, these guys are orthonormal. The metric takes that form. And so all we have to do in order to generate an orthonormal basis for every point of the manifold is, for every point of the manifold, we choose a Riemann normal coordinate system. And then look at the dx mu at the origin, and these are an orthonormal basis. In practice, that's not how you do it, but this proves that it always exists. Yep?
Can you find a coordinate chart so that the metric is eta on the whole chart and not just at a point?
Exactly, that's what I'm just proving here.
But you're saying so this only holds at one point in the chart. It doesn't hold on the entire chart. Right?
Oh, I see. No. Okay, we have to be careful here. If the E mu's are chosen to be the dx mu coming with a coordinate system, so if in an entire chart the E mu are these, then in general you can only achieve this at the origin of a Riemann normal coordinate system. You can only achieve it at isolated points. But forget about coordinate systems. Our aim here is to simply choose at every point of the manifold a basis in the cotangent space such that the metric takes this form. Right? Nothing to do with coordinate system. We just want to know, is there at every point of the manifold a set of cotangent basis vectors such that the metric at that point takes this form? And the answer is yes, because at that point in question we can choose the dx mu of a Riemann normal coordinate system centered at that point. And then, can we do it at another point? Sure. Also, another point is the origin of some other Riemann normal coordinate system. And so we can get it for all points. So, in general, they will not be the dx mu of any coordinate system, right? They can only be the dx mu of a coordinate system at one point or at some isolated points, but in general they won't be. But we free ourselves from choices of coordinates. I only appealed to Riemann normal coordinate systems to prove the existence of those bases in the cotangent space, but we don't actually need the Riemann normal coordinate systems. You can use a coordinate system that's nowhere a Riemann normal coordinate system and still use at every point an orthonormal basis of cotangent vectors. Now, is that unique? For a given space-time given by a differentiable manifold and a metric tensor on it, any orthonormal frame yields a new orthonormal frame under the following condition. If the theta nu of x is a bunch of orthonormal cotangent vectors, and we change bases, so this used to be called A, now I'm calling it lambda for a reason that will become clear a little later. So we do a change of bases, a general position-dependent change of bases, and we get a new bunch of basis vectors in the cotangent space. And then if these are orthonormal, let's ask, is it possible to have these orthonormal as well? Now, what does that require? Well, that requires that this tensor is that tensor, right? So we want that the metric is eta AB in the one basis, and the metric is eta mu nu in the other basis. And if you plug that in here, you find that that requires that this linear map be such that when you use it to transform both indices of the eta, so you transform the eta mu and the mu index and the nu index, then you get the eta again. So the answer is there exist other orthonormal bases if we can find matrices like this, in general position-dependent matrices like this, which have the property that when they transform that eta matrix, they leave the eta matrix the same. And I hope you remember that this is the condition that defines Lorentz transformations. Lorentz transformations are those linear maps which preserve the special relativistic metric, expression for the metric, I should say. So what we see here is that no, the choice of orthonormal frame is not unique. If you have a choice of orthonormal frame, you obtain a new orthonormal frame by doing Lorentz transformations. And you can do a different Lorentz transformation at different points in space and time if you want. Yep?
So it's easy to see that at every point we can pick an orthonormal basis. Is there any constraints we can say on how smooth the going from one place to another, this global?
I will assume throughout that it's smooth. In principle, if all you care about is the orthonormality, then it wouldn't have to be smooth. That's right. This lambda mu nu of x could be jumping around. It wouldn't change that fact that you go from orthonormal to orthonormal, but in practice, we will assume this to be smooth. You see, otherwise you would get in trouble with definitions such as those of the affine connection, because the affine connection transforms with derivatives of that. It doesn't just transform, you see, all tensors have simply powers of that matrix in them. When you change basis, the coefficient functions, the scalar coefficient functions of the tensors will transform with those matrices, or with the inverse of that matrix, depending on whether it is a contravariant or covariant index. But the affine connection doesn't. The affine connection has a tensorial behavior of transformation, plus it has a term that involves also derivatives of that change of basis matrix. If you remember from earlier, where is it? Here. You see? This is the tensorial part, but it also has this transformation behavior, and that involves derivatives. And that we couldn't do if it weren't smooth. Okay. So what we see here is that orthonormal frames are unique up to local Lorentz transformations. And we are used to the fact from special relativity that the laws of nature can be written down in one coordinate system, or, in one freely falling coordinate system, in one Minkowski space orthogonal frame, or you can Lorentz transform, and then you get the same laws. That's the whole point of special relativity, the invariance under Lorentz transformations. But if you remember, special relativity never allows you to do local Lorentz transformations. You see, you always have to do a global Lorentz transformation. You change into a coordinate system of somebody who's moving with a certain velocity, let's say. But you can't, in special relativity, simply do a local Lorentz transformation. Here you boost this much, and there you boost that much. That would change the shape of the laws. Special relativity is not invariant under that. And the fact that we can here do it with local Lorentz invariance, we will come back to later today, because that's related to the gauge principle. Okay, so frames are unique up to local Lorentz transformations. Now, let us re-express the degrees of freedom of gravity. We used, by using that formalism now, we used to specify a space-time. We used to specify the curvature of space-time, and remember the essay, how do you express curvature? We used to express the curvature of space-time through these data, a differentiable manifold and a metric on it. Now, instead, we will specify a space-time and its curvature through giving these data a differentiable manifold and an orthonormal frame. So let's assume, let's carry this through. Let's see how we can shift the encoding of the curvature information in here, or the shape information of the space-time in the G, how we can shift that to the theta. And by that I mean, once you give the metric tensor, you can then calculate what the Christoffel symbols are. You can calculate the curvature tensor, the action, the equations of motion, the Einstein equation, right? Here we want to be able to do the same thing. You give yourself the orthonormal frame, and then from that you should be able to calculate everything. You should be able to calculate what the Christoffel symbols are, or really the curvature, the connection one form. You should be able to calculate that from there. You should be able to calculate the curvature two form, the torsion, if there was one, but we assume it's vanishing. We should be able to express the Einstein action in this way. We should be able to express the Einstein equation in terms of those data. And by the way, we should also be able to express the metric in this term, in this way, right? So this should be, what I'm claiming is that we can view this as primary, but we can also view this as primary, and then derive everything else from that. So how do we do that? What's the cascade? Starting from that, how can we calculate everything else? Okay, so we start out by choosing our orthonormal frame. That corresponds to, in the earlier business, choosing this, right? Choosing the metric is to choose the space-time. Now, choosing those guys is to choose the space-time. How can we do it? Well, instead of giving ourselves a g mu of x, we have to give ourselves a theta I of x. So we choose a coordinate system, and then we choose our orthonormal frame, the theta mu of x, given by these functions. They encode now everything about the space-time. Right? You choose a coordinate system, you choose those functions, that determines your choice of orthonormal frame. And once you have the orthonormal frame, the claim is everything is calculable. Curvature, connection, all of this. So in practice, you can just go and specify, just for the heck of it, choose a coordinate system, cook up some function, arbitrary really, and then say, a matrix valued function, and then say these guys are orthonormal. Claim that the metric with respect to this basis at every point takes this form. Okay? Then you have specified implicitly, or explicitly actually, you have specified a space-time manifold in this way. So let's see. Let's see whether that's really equivalent to specifying the metric. Obviously, if we are right, then we should be able to calculate the metric from this. So knowing those functions a mu nu of x, or choosing them really, we should be able to reconstruct or construct what the metric tensor is from that, if the functions a mu nu of x really contain all of the information. And by reconstructing the metric tensor, I mean reconstructing it in the basis that comes with a coordinate system. Because obviously the metric tensor is already here. That's what it is, right? There's nothing much to reconstruct. Here it is. In this basis, that's the metric tensor. There's nothing else to be said about it. Except you may want to know what the metric tensor looks like when you choose not this basis, but when you choose this basis that comes along with the coordinate system. How does it look like? Well, easy. Remember that the metric tensor is the metric tensor, independently of any choices of bases and independently of any choice of coordinate system. It's the same object. So we can write it in this way. Remember, this is an orthonormal frame. So, because it's orthonormal, the metric takes this form. On the other hand, we do know that the theta are linearly related to the dx mu. So we just use this expression here, this one, to express the thetas in terms of the dx. So you see, the g is this, because the theta are an orthonormal frame. The theta is then expressed in terms of a dx. And so you see that overall, the g is therefore now expressed in this way, in terms of the tensor product of a dx mu and dx nu with coefficient functions given by this, by the eta a. So we have now found for this information what that information is. The g mu nu of x is given by eta mu nu contracted with those two a functions. In other words, the a is something like the square root of the metric. You have to sort of square it in order to get the metric. Okay, so this is the equation that we obtain. The metric tensor written in the basis that comes along with the coordinate system is given by this expression where the a map us from that coordinate system to the orthonormal frame. So indeed, choosing that basis determines the metric in the old-fashioned way, even though really the metric is also this, right? And you can already foresee how much this will simplify everything. For example, in all formulas, almost all of them, we used to have some square root of determinant of the absolute value of, we used to have the square root of g, right? Which is really the square root of the absolute value of the determinant of g. This is 1 now. It's always 1, because eta is, because g is represented as the eta, and that's always having determinant minus 1, absolute value is 1, square root of that is 1. So this, for example, will be very much simplified. Okay, so we conclude that the shape information about the space-time is encoded in those functions. Okay, so this is how the cascade starts. This is how we define a space-time, okay, is how we can define a space-time, and that then should allow us to calculate not just the metric, but it should allow us to calculate those structure coefficients. I'll remind you in a moment what they are. It should allow us to calculate the connection 1 form and the curvature 2 form. And therefore, we should be able to express everything in terms of these data. Not that it is always convenient to do this, but as a matter of principle, we should be able to do that. Okay, so here's now this cascade, how we go from that to this, to this, to this. Here's the definition of the orthonormal frame in terms of the coordinate basis, coordinate-induced basis of the tangent space, cotangent space. Then, remember those structure coefficients? We have the Ci, j, k of x. What are they? By definition, these are the functions which make that equation true. So take our orthonormal frame, and these are cotangent vectors, right? Take the d of that. The d of a cotangent vector is going to be a 2 form. And because it is a 2 form, it has to be expandable in that basis, because these guys form a basis in the space of 2 forms. And the expansion coefficients, these are those c. If we had chosen for the thetas to be the dx mu, well, then that would be just 0, right? The d of the d is 0. But our theta I of x, our orthonormal frame, is generally not a coordinate-induced choice of basis. So in general, this is not vanishing, because the theta is not the d of anything. And therefore, there will be some non-trivial expansion coefficients of that expression here. Let's work it out. I think I left it to you as an exercise some lectures ago. Here's the solution to it. So we calculate what the d theta is. Well, what we have to do is, here is the expression, here's theta, and we calculate the d of it. Now, to calculate the d of it is to calculate the d of that 1 form, where this is a 1 form and that is a scalar function in front. So we have to calculate the d of all of this. By the Leibniz rule, it's the d of this times that, plus leaving that the same, and the d of this. The second term is vanishing because it's the dd, right? The d of dx j. So we only have to take the d of this. And that's what we have here. It's the aij, k dxk. That's the d of a. Just the ordinary derivatives and then multiplied with the dxk, veg dxj. And we compare that with the expansion coefficient. We can read off what the expansion coefficients therefore are. We must have that, because this is equal to that, we must have that the minus 1/2 times this business is all of this. And from that we can then solve for the expansion coefficients, and we obtain that the c are given by the derivatives of the A and also inverses of the A matrices. Okay, so we've done the first step. We've calculated from those initial data that specify the space-time, those coefficients here in that equation. They're not in themselves very interesting, but very useful. Because now in the next step, we can use them to calculate the connection. Okay, so the C coefficients are already expressed in terms of the A's. Now from a few lectures back, I think lecture 11, yes, lecture 11, we had an expression of the Christoffel symbols in an arbitrary choice of bases in the tangent spaces. It was all of this. If you make an arbitrary choice in each cotangent space and each tangent space, then the Christoffel symbols take this complicated form. But we're not making an arbitrary choice. We are making an orthonormal choice, where the metric tensor is always eta mu nu at every point in the manifold. And that means that those derivative terms all go away. Remember that if, on the other hand, we chose to work with the bases in the contention space, that comes with the coordinate system, if we chose to work with the dx mu, then it would be the opposite situation. All of these terms would go away, and only those would remain. That's the traditional thing that you get before you work with frames, right? And why would they go away? Well, they go away because the c's are vanishing when you work with the basis that comes with the coordinate system. Why? Well, because remember that when the thetas are just the dx mu, then the d of that is 0, so therefore all of the c coefficients has to vanish, right? So if this is dx mu, then d squared x mu is 0, so the right-hand side is 0, so the c coefficients are 0. Okay, so the general formula for Christoffel symbols is this. If we choose an orthonormal frame, then the g is always eta, the derivatives vanish, though the terms with the commas, they go away, and we're just left with this expression. Okay, and remember that the metric now is just the eta, easy, and the c coefficients are given by the equation just above. So it's not actually as complicated as it may look, because these guys are trivial. So it's really just a combination of the c's. Actually, in what follows today, I will often keep g, even though it reduces to eta, just to see how often things simplify. Because when you have a square root of g still around, you can always just say, oh, great, this simplifies now, it's just 1. Okay, so now the next step. From the Christoffel symbols, we get the connection 1 form. That was easy. We simply take the Christoffel symbol and declare one of its indices, one of its lower indices, to be that of a 1 form. And there we go. This is the connection 1 form. And then, once we have the connection, we can write down what the curvature 2 form is. And for that purpose, we can use the second structure equation. Second structure equation was expressing the curvature 2 form in terms of the connection, if you remember. Actually, let me remind you of these things. But for now, before I remind you of the structure equations and the Bianchi identities, let me just give you the gist of this. We arrived at our goal now. We expressed space-time in terms, the shape of the space-time in terms of this matrix-valued function a mu nu of x, which gave us an orthonormal frame. And then we've been able to calculate from that the metric, if we so choose, in whatever basis we want. We get the affine connection, we get the curvature, we get the connection 1 form, and we get the curvature 2 form, and that means we have everything. We can now, in principle, write down the action and equations of motion, all of those things. But that may have been a bit quick, the last step. How did we go so quickly from the connection 1 form to the curvature tensor, or to the curvature 2 form? Well, that was the second structure equation. Let me remind you of these key equations. There are 4 of them. 4 key equations. 2 structure equations and 2 Bianchi identities. Those guys are basically definitions. And the Bianchi identities are a consequence of diffeomorphism invariance. So what are these the definitions of? Well, the first structure equation is the definition of the torsion. And the second structure equation is the definition of the curvature. The first structure equation is that the torsion is the absolute covariant derivative of our frame, of our basis of 1 forms. And that is, because of the definition of the capital D, this expression here. And in general relativity, we assume that the torsion is equal to 0. So we obtain that this is equal to 0. And in practice, what we will remember from that is this part. This part. That this expression here is equal to 0. It's really the torsion. but it's nice to know that this expression is 0. Anyway. You may wonder why this doesn't look like the torsion. I mean, why is that the torsion? There's a simple way to see how this reduces to what we are used to thinking of the torsion. You remember when we first encountered the torsion? We first encountered it as a possible antisymmetric part of the Christoffel symbol, right? And then we said, okay, the symmetric part is the one that encodes curvature, that encodes gravity, and the antisymmetric part we said, well, that's torsion, and we argued it away. Imagine if you choose for your theta the basis that comes with the coordinate system, the dx mu. In this case, this term is absent, right? Because if the theta is dx mu, then we have a d squared vanishing. Okay, so if we go with the usual coordinates choice of basis in the cotangent space, that term is absent. And then here we just have the dx mu. And here, what do we have? Here we have basically Christoffel symbols. And because of the wedge product, we have an antisymmetric combination. So what this is saying is that the antisymmetric part of the Christoffel symbol is vanishing, right? So this equation is really just boiling down to what we were initially encountering, namely that in that choice of basis, the antisymmetric part of the Christoffel symbol is vanishing. But this is the covariant version of that statement when we free ourselves of coordinate systems and choices of bases in tangent and cotangent spaces. Now, the second structure equation is also a definition, right? This first structure equation, definition of torsion, equal to 0. Therefore, gives us a nice non-trivial equation. Second structure equation is basically just a definition of the curvature tensor, and it is this. Again, you may wonder, that doesn't look like how we first encountered the Riemann curvature tensor. It is. Remember, this is basically the Riemann curvature tensor with two extra indices suppressed because we consider them to be part of a two-form. The Riemann curvature tensor has 4 indices, right? And the 2 last indices we considered to be the indices of a two-form. The omega is the Christoffel symbol. The d of it gives us derivatives of the Christoffel symbol. And this is Christoffel times Christoffel, if you spell it out in tensors again, not in forms, but in tensors. So what we have here is derivatives of the Riemann curvature of the Christoffel symbol, and here we have products of 2 Christoffel symbols. And now it may look familiar. The curvature tensor is an expression in terms of first derivatives of the Christoffel symbols plus something quadratic in the Christoffel symbols. That's just the most general formulation of that, free of the choice of coordinate system, free of the choice of bases in the tangent and cotangent spaces. And then we also proved some lectures ago that the Bianchi identities hold, the 2 Bianchi identities for the curvature tensor, and the torsion would occur on the right-hand side, but it is vanishing, so the Bianchi identities are relatively simple. And they basically translate into certain symmetry and anti-symmetry properties of the curvature tensor. And also, as we will show later on, and as will be important later on, if we choose our frame to be orthonormal, then the connection 1 form will be antisymmetric if you lower both indices. And at the moment, this may not look so important, but it will be important later on when we will connect general relativity to the concept of gauge theory. Okay, so now that we have expressed all of the quantities that we need in differential geometry in terms of the frame rather than in terms of the metric, we should be able to re-express the Einstein action in this new language, in terms of these new degrees of freedom, in terms of the theta, and the equations of motion, the Einstein equation as well. So let's do that. So here's the Einstein action that we arrived at in the previous lecture. Let's analyze what we have. up to a prefactor, which is just numerical. We have here the Ricci scalar, total contraction of all the indices of the Riemann tensor. And then we have square root of g d4x. Now this is a zero form. It's just a function, scalar function, it's a zero form. And that is a 4 form. It's the volume form. So really what we have is 0 form times 4 form, which is a 4 form, and that can be integrated over 4-dimensional space-time. We can rewrite that a little bit. Remember the Hodge star operation. It maps p forms into n minus p forms. In particular, it maps 0 forms into n forms. In the case of space-time, it maps 0 forms into 4 forms. Here's the definition of it. Imagine, consider a p form. Nu is a p form. So here is a basis in the space of p forms. These are the coefficient functions. Then the Hodge star is an n minus, the Hodge star of nu is an n minus p form. And it's obtained in the following way. If you remember, the Hodge star operates this way. You take your p form, consider it as a p-fold covariant tensor. Then you raise the indices using the metric to obtain a p-fold contravariant tensor. And here are its coefficient functions. And then that p-fold contravariant tensor you feed as input into the volume form, which takes up to n inputs. But you're feeding it only p inputs. So the volume form still has n minus p open slots, which leaves it an n minus p form. So p-fold covariant, raise the indices, then it's a p-fold contravariant tensor. Then you contract with the volume form, which has n indices. You contract the p with the n. You're left with n minus p indices, which are lower. So you end up with an n minus p form. Okay, so the Hodge star maps p forms into n minus p forms. And comparing with what we have above, we see that in the special case where we have a 0 form, it's going to be mapped into an n form. And in particular, a 0 form simply acquires this square root of g because there's none of this epsilon business then. I mean, this is just, for 0 form, the nu, there's nothing to be lifted there. So another way of writing the Einstein action is to say that it's up to the prefactor, the Hodge star, of that 0 form. Right? Because for 0 form, the Hodge star simply attaches the volume form to it. So that turns the 0 form into a 4 form with the volume. Okay, it's just another way of writing the Einstein action. But we don't want to have R involved at all. We want the curvature 2 form involved. So let's express the Einstein action in terms of our initial data, namely the frame, and in terms of the curvature 2 tensor, which itself we can express in terms of the theta. For that, it is useful to define 2 tensors here, just because otherwise the formulas get a little lengthy. Take 2 frame basis vectors, take the wedge product of them, that's a 2 form then. And the Hodge star of that is also a 2 form. And that 2 form we call H alpha beta. Actually, it's a capital eta, but indistinguishable from Latin H. And when we take 3 frame vectors, we get a 3 form. Take the Hodge star of that, it's a 1 form. And that is that 1 form here. Explicitly, the H alpha beta is that expression as a 2 form, and the H alpha beta gamma is this expression as a 1 form. Then the proposition is that the Hodge star on R the 4 form that makes the Einstein action, is given by the wedge product of this h mu nu, of this 2 form, so basically 2 of those thetas, and the curvature 2 form. Which means that the Einstein action now takes this form here.
Excuse me.
Yep.
Where does the prefactor of 1/2 come from?
Let me see. Here, 1 over p factorial.
Put the second equation down there. Why do you get 1/2?
Sorry, which one? Here? I mean, this is from the ones we... Further down?
The second one, yeah. No, the one you're pointing at.
Oh, this one, yes.
Why do you get 1/2?
Oh. Oh, good point. That may not be right. Yeah, I'll check that later. Yeah, that may not be right. Because, yeah, that's right. This should be either a 6 or a 1. Right? Because it's 1 over p factorial. Yep. Okay, thanks. Okay, so we have now expressed the Einstein action in terms of this product of 2 frame vectors and the curvature scalar, curvature 2 tensor. In view of the time, maybe we need not prove that in detail. Well, I don't know. Should we do that? Ah, that feels better. No, let us skip this. Let us skip this proof. Let's move on to the main proposition, namely how to go then from the Einstein action to the Einstein equation, right? So we have re-expressed now the Einstein action. We should be able to re-express or rederive the Einstein equation now. And remember how we used to do that. We used to do that by expressing the Einstein action in terms of ultimately the metric. And then we varied the action with respect to the metric. We differentiated the action with respect to the metric in order to obtain the equation of motion for the metric, which was the Einstein equation. Now our fundamental degrees of freedom are these A matrices, or really the theta. So now we are varying the theta. So it's a slightly different variational principle. Okay, so the main proposition now is this, that if we vary the action with respect to the theta mu of x by changing the frame in an arbitrary way, we obtain that the variation of the Einstein action is the variation of the first term in it, leaving the second the same. Sorry, this is already the proposition. So the variation of the Einstein action turns out to be this expression here, where it's something that we have to prove plus the d of something. And of course, we do the variation of this, right? So we have to vary the Einstein action with respect to theta. So we have to calculate how this varies with theta and how that varies with theta. And the claim is that if you do this, you find that the variation of the Einstein action is actually this expression, where I can write d of something because it doesn't matter what's in there, because it's a d of something. When you integrate it, the action is, of course, the integral over all of this. This is just the integrand. When you integrate it, then you get a boundary term. And if you go far out enough, you can assume that that boundary term is vanishing because we are not varying outside a certain finite region. And this then means that the variation of the Einstein action is given by the integral over all of this business here, plus, the boundary of that term, and as I just said, that will not contribute, and we are just left with this. And that is supposed to vanish for all variations of the theta, and so that gives us then the left-hand side of the Einstein equation, this piece, the eta mu nu rho, which is just a decorated version of the theta. Remember what the h with the 3 indices was? H with the 3 indices is just some decorations times the theta. And in the case of an orthonormal frame, this even is just the 1. So what we obtain is that the left-hand side of the Einstein equation, the differentiation of the Einstein action with respect to theta mu, is just this expression here. Now let's look at the energy momentum tensor for the right-hand side of the Einstein equation. So when we express the matter action in terms of tensor valued forms, then we differentiate with respect to theta, then we can obtain a definition of an energy momentum tensor. I don't know if can you see that this is the same as how we defined the energy momentum tensor in the previous lecture, right? It's like ds by d theta, and then that is the t mu nu. There is just a small difference here. The only difference is really that the t mu nu, the energy momentum tensor, is usually thought of as being a twofold covariant symmetric tensor. But it is more natural in this framework to view the energy momentum tensor as a 0-1 tensor valued 1 form. In other words, one of its lower indices is considered to be a 1 form. That's why it looks a bit amputated here. It has only 1 index instead of the usual 2. And so that is the expression that occurs in here. It's a 1 form with respect to the suppressed index, and that gives us a 3 form. And then that is a 1 form, so the whole thing is a 4 form that can be integrated. So overall then, the equation of motion, the Einstein equation, is obtained by varying the entire gravity action and the matter action with respect to the frame, setting that equal to 0. The left-hand side of the Einstein equation takes this form, the right-hand side takes that form, where again, this is just a fancy way of writing what we knew before. It's just 8 pi g t mu nu, but lower index considered a 1 form. The star makes it a 3 form. On the left-hand side, we also have a 3 form because the curvature tensor is it's a 2 form. The curvature 2 form, and that, remember, is just a 1 form. So it's 3 forms all the way. So the Einstein equation is actually a 0-1 tensor valued 3 form equation. 0-1 tensor valued, 1 lower index. It's a 0-1 tensor valued equation for 3 forms. I leave it to you as an exercise to amend the equation so that it includes the cosmological constant. Try to figure that out. Okay. One often also then defines the Einstein form. So basically, we just give this whole thing on the left-hand side a new name, and that is the Einstein form. So this entire thing is defined to be the Hodge star of G. Remember, that's a 3-form equation. If we define the G to be the star of that, the G is a 1 form. And so then what we have is a star G equal to or proportional to star T. So we can star the entire equation. And then we just have a G mu equal 8 pi G T mu, where the G mu is the Einstein form. So now the Einstein equation is a 0, 1 tensor valued one-form equation, which is what had to be expected. Because if you remember, the Einstein equation used to be G mu nu equal to 8 pi G T mu nu. And that is having two covariant indices, and we're simply declaring one of them to be a one-form. So we're arriving back to, we see that it's the same theory that we're describing in this way, even though we varied slightly differently. Now the next slides are proof of this, and it's a little tedious, but I think I gave you all the details in here, so I leave it to you to work through that at home. And if you have if you get stuck anywhere in this proof, then let me know and I'll explain it. I think it's more interesting if we now focus on general relativity as a gauge theory. Yep.
So in the one-form formulation, there's different degrees of freedom in that. If we're just doing counting arguments, when we're dealing with the a two tensor that has a symmetric two tensor, we have 10 degrees freedom. Now it's kind of hidden, and now it's just these four. And then I guess the forms also have some hidden.
That's right. Yes.
So is there an easy way to see where these degrees of freedom have gone?
No, there's no mystery about it. I mean, it's literally that. Once we arrive at that point, you can easily reformulate this again in terms of symmetric two tensors. So there's nothing, it's really just a suppressed index at that point. But remember that we derived the original formulation of the Einstein equation, always assuming that we would choose as the basis in the tangent and cotangent spaces the one that came through the coordinate system, right? And now we are completely free about this. Okay, but I couldn't help but adding a few slides last night about general relativity as a gauge theory. And also because some of you may not be all that familiar with what a gauge theory is. So let me give you the gist of it. I can't go into much detail, but I hope the gist of it becomes clear. Okay, so let's take stock. Where did we arrive? We found that the Einstein action can be written in this form, right? This is a two-form, the whole thing is a four-form integrable over four-dimensional space-time. And the Einstein equation takes this form, okay? And the nice thing about this is that we now have a theory, and I'd like to stress that, which is not just having the same action, the same formulation of the action, the same formulation of the equations of motion, no matter what coordinate system you choose. No, these equations don't even change if you change the choice of bases in your tangent and cotangent spaces. It's completely agnostic to that, right? You can choose whichever you want. So we have that invariance here. So these equations are the same also when you change from one frame via a linear transformation to another frame. So the thetas are some orthonormal bases. You change orthonormal bases to a new orthonormal basis, theta tilde, and you can do that with a different Lorentz transformation at every point in space, and the equations won't care. It's taken care of. It's just choice of bases, and choice of bases, I mean, we made sure that we're dealing with tensors and with objects that are not defined relative to any coordinate system or relative to any choice of bases. That's why these equations are automatically the same, even when you change in this way. And remember, that is a difference, because you can't do that to a special relativistic theory. You could only do global Lorentz transformations, but not global ones. So the upshot of this is that in principle, what we could do is this. We could start with a matter theory, for example, the Dirac equation, or the Klein-Gordon equation, or the Maxwell equations, or all of them together in Minkowski space, a special relativistic theory. And this original theory of electromagnetism and electrons, Dirac equation, and so on, that original theory will be special relativistically invariant. So if you do a global Lorentz transformation, you get the same theory, same equations of motion, same action, right? But not if you do local Lorentz transformations. The theory cannot handle that. What we showed here so far in this course is that, yes, you can do it. You can make that theory invariant under even local Lorentz transformations, local changes of basis in the tangent and cotangent spaces, but you have to use that formalism, and in particular, you have to use a covariant derivative now. The covariant derivative was very important in this. And the covariant derivative had the Christoffel symbols in it. And the Christoffel symbols encoded gravity. So, in summary, just to make a long story short, you start out with a matter theory, such as the Dirac equation, or Klein-Gordon equation, or Maxwell equation, which has a global Lorentz symmetry, and then you require that it becomes a local Lorentz symmetry. You can achieve that, but you have to change your notion of derivative to a covariant derivative. And in the process, you're introducing a new force, gravity. This is very similar, very analogous to the gauge principle in particle physics. In particle physics, the gauge principle works this way. You write down a theory which has a global symmetry. And then you do what is called gauging. You gauge it so that this symmetry becomes a local symmetry. You can achieve that by turning derivatives into so-called covariant derivatives. And in the process, you have to introduce something that's similar to the Christoffel symbols, a new kind of field. And that new kind of field is some new physical degree of freedom, which can be, in particular, just like the Christoffel symbol introduces gravity, these new Christoffel-like things, these new affine connections, will introduce other forces, the electromagnetic force, the weak force, and the strong force. They all arise in this way. While the electromagnetic and the strong force arise in very, very similar ways that I will review now, and gravity is somewhat similar, but not the same. Okay, so here's the gauge principle of particle physics. This is special relativity. You could do this also covariantly now, but I'd like to keep things simple. So this is special relativity still. Consider the action of a Dirac field. So here we have a Dirac spinner, same Dirac spinner, I times the gamma matrices, ordinary derivatives minus m. M is the mass of the particle. So that's the Dirac action. The Dirac action has a global symmetry. Namely, if you take your Dirac... Oh, by the way, I should say that each of those spinners has an index which runs from 1 to 4. Remember that spinners are 4-component vectors. I'm suppressing that index. It's not important for what is needed here. But you need to keep in mind that these are 4 vectors because the gamma matrices are 4x4 matrices which act on that. So in principle, there's a Kronecker delta here. This is an identity, mass times the identity matrix on that spinor space. Here's the spinor space. And and here you have a 4x4 matrix. But let's suppress that. It's not important for the discussion that follows now. Okay, so here we have a spinor field, and that in particular has a complex conjugation in it. There's also a gamma 0 matrix, but it doesn't matter. Here we have psi, and here we have a complex conjugation of psi. This action has a symmetry, a global symmetry. Namely, if we take a spinor and we turn it into a spinor tilde, a new spinor, which is the same as the old one, except that we multiply it with a phase. e to the power of I alpha, where alpha is some real number. If we do that, then we obtain a new field psi, and the psi bar turns into the same as before, but with a factor of e to the power of minus I alpha, because the bar involves a complex conjugation. Well, then we can see that clearly the action is invariant under that global gauge transformation, because the psi picks up the phase e to the power I alpha, but the psi bar picks up a phase e to the power of minus I alpha, and there's just a number here and the opposite of that number over there, but it pulls through all of this, cancels away, the action is invariant. So what we have is that the action for psi is mapped into the action for psi tilde, which is the action for psi again. Just because this factor cancels that factor, because one of them comes here, one of them there, and this factor just moves through, it's just a number. However, the Dirac action is not having a local symmetry. You see, if we map psi of x into psi tilde of x, which is e to the power of I alpha of x, if that alpha is space-time dependent, and then the psi bar has a similar inverse phase, then the action of the Dirac action goes into the Dirac action of psi tilde, which is not the original action. The reason is that this derivative will act not only on psi, but no, it will now also be caught up on differentiating this. Okay? So we get that the action is the old action plus an extra term which involves the derivative of alpha. How can we fix this? So, how can we fix this? Well, this is what the gauge principle does. The gauge principle says that we can fix it, namely by introducing a new field a mu of x, which transforms such as to absorb the extra term that arises from differentiating the alpha. So the idea is that we start with the Dirac action, and then we replace the d by dx mu by a new so-called covariant derivative, which involves a new kind of field, very similar to how the Christoffel symbol arises in general relativity. So we replace the d mu here by this expression, by d mu plus I times a mu of x. A mu of x is a new field that we just pulled out of the hat, just like the Christoffel symbols just appeared in general relativity. And we fix it, and the whole thing will be called a covariant derivative. And of course it will be technically an affine connection and all of that. But we fix it in such a way that we determine the a mu of x to be such that it has particular transformation properties. Namely, as we map psi of x into psi tilde of x with this local gauging, at the same time we map a mu of x into a mu tilde of x, which is the old a mu of x minus I d mu alpha of x. If we do this, well then, what about the action? Okay, so the action now depends on two fields, psi, the fermion field, the electron field, and A. And we map it now into the action of psi tilde and A tilde. So we have the psi bar picking up this local phase. We have that the derivative is the covariant derivative, but the A is picking up this extra term, so we get this extra term here. And here we have e to the power I alpha of x psi, that's the local gauge transformation of the psi. And you see, this is now the old action again. The reason is that this derivative will not only act on the psi as it should, it will also act on this, therefore will produce a term I derivative of alpha of x, which used to destroy the symmetry. But that's exactly the term that the A produced here under its transformation, so it goes away. I mean, with an opposite sign, so it goes away. So the whole thing is symmetric. So on balance, what happened is that we started with a theory that had no A field in it, and a theory that had a global symmetry. We made it a local symmetry by changing the derivative to the covariant derivative, by introducing a new field A, which has this transformation property, and then we have a local symmetry. But what is that field? In the case of gravity, the Christoffel symbols gave us gravity, but here the A mu, in this case, gives us electromagnetism. It turns out that this is the way that the electromagnetic four-vector field is coupled to the Dirac electrons, or Dirac quarks. And then we only need to write down now an action for the A's themselves. You see, this is an interaction term between the psi field and the A field, but we still need some term quadratic in the A and time derivatives in A, which is the F menu or F menu. That's an extra action. But what we've already seen here is that if you gauge the Dirac field, you get electromagnetism. You can derive it, so to speak. When that was realized in the, I think, 40s, they thought, that's great. Can we generalize that? Of course, they had at the time no idea that general relativity is of this form too. But they said, can we generalize this? And then I think it took the 50s and the 60s to do it. But conceptually, it's actually not that hard. There's a generalization to so-called Yang-Mills theory, and it works like this. Remember, when we map psi of x into psi of x times a phase, and introduce a field A mu of x, then we obtain the electromagnetic field, and technically speaking, e to the power of I alpha of x is an element of the group U1. The group U1, which is simply the set of all complex numbers which obey that their complex conjugation is their inverse. It's just another way of saying that they are phases. But they are a group, right? If you multiply two phases, you get another phase. Every phase has an inverse phase. And there's a neutral element in that group, which is 1. So U1 is a group. Topologically, it's a circle. And so they thought, what if we go to higher rank groups? This is U1. What about U2 or SU2 or SU3? Well, you can do this. So now you consider the Dirac equation again. But let's say that the psi have some extra index. Some extra index which runs from 1 to n, from 1 to capital N. Nothing to do with space-time dimensions. It has nothing to do with the tangent space or cotangent space. It's just a new space that's been invented. So let's say that our fermion fields, our electron or quark fields, have some extra index which runs from 1 to capital N. So here's the index, there is that index, and then the mass term just has a Kronecker delta of AB, and of course twice occurring indices are again to be summed over. Here too we have a Kronecker delta AB in there. So you see, if we have a Dirac theory that is like this, it too will have a global symmetry, which is now, however, a bigger symmetry. Namely, we can now map these, let's say that the psi, it's basically an element of c to the power n, right? It's a vector with capital N entries, and each entry is a complex number. So now we are mapping with the global transformation the psi vector. Actually, these guys are called isospinors. We are mapping such an isospinor into a certain group element that's a matrix times the original spinor. So instead of multiplying simply with the phase, we are now multiplying with this matrix. And that matrix is chosen from the group SUN, where the group SUN is the special unitary group, And it's the set of all matrices, of all n by n matrices with complex entries, which have the property that they are unitary. So they have the property that G dagger is equal to G inverse, and the determinant is equal to 1. That determinant equal to 1, that accounts for the S here. It wouldn't be necessary to put that S here to require the determinant to be equal to 1, but it turns out that for physical applications, the S is there. Okay, so that's a global symmetry. Why? Well, because if you multiply with that G matrix here, you get a G dagger because of the psi bar, and here you get a G, and you can move that G through because it's not space dependent. You can move that G through, and the G dagger G is canceling itself. You just get the identity matrix, so that Dirac action has a global SUN symmetry, but not a local SUN symmetry. If you make your gauge transformation space-dependent, then it's just like having a space-time dependent phase. And the derivative picks up on that. And you can fix this in the same way that we fixed it earlier. Namely, we can introduce now a new derivative. Instead of the ordinary derivative, we have now a new covariant derivative, where this stuff is playing the role of a Christoffel symbol. But it's a bit more complicated now, because we're no longer dealing with just numbers. We're dealing with matrices here. Also, this extra field is now matrix valued. So this is really just a number valued here. It has an index mu, which is a space-time index, same as this one. But it also has an index r. And then here's a basis in the space of matrices that we'll be dealing with. And this whole thing now is a covariant derivative. And it turns out that if you give the B the right transformation properties along with that transformation property, then the action of the Dirac, the Dirac action is again invariant under the combined transformations of this gauging and that gauging of the B field. Now you may wonder what is that? Well, if you choose n to be 2, so if your isospinors are two component spinors, then you get the weak interaction. Not directly, the weak interaction really is a mix between the electromagnetic, between the U1 and the SU2. But roughly speaking, you can say that. You can say that if you choose n equal 2, you get the weak interaction. If you choose n equals 3, so you have the gauge group SU3, then you get the strong interaction. You get QCD. So in practice, particles such as quarks have very complicated derivatives because they have the ordinary derivative. And then they will feel the weak interaction, they will feel the strong interaction, and they will feel gravity. So the total covariant derivative has lots of terms there. And what are these guys here? Well, these guys here are generators of the group SUN. They're infinitesimal generators of the group SUN. They are elements, bases in the Lie algebra of SUN. It's not important for our purposes now what exactly these things are, but I'd like to point out that for gravity, it's again very similar. Just like for QCD, or the weak interaction, you have here the generators of the Lie algebra of the symmetry group, such as SU2 or SU3. In the case of gravity, our covariant derivative has here the Christoffel symbols, or really the connection 1 form. And the connection 1 form is actually also Lie algebra valued. The connection 1 form takes its values in the infinitesimal Lorentz transformations, just like these guys are taking values in the infinitesimal SU2 or SU3 transformations in that Lie algebra, so in gravity too. So what we have here is this, switching back to gravity now. The gravity action can be written in this form, the Einstein equation in that form. And these equations are now invariant, just the same way that the Dirac action with all the trimmings, with all the A fields, B fields, the Dirac action is invariant under local gauge transformations. The gravity action is invariant, and the Einstein equation is invariant under even local changes in the choice of basis of the tangent spaces, which is to say, even under local Lorentz transformations. So we can allow ourselves to go from one frame to another frame with local Lorentz transformations. And now remember, our covariant derivative is this. And if you apply that covariant derivative to a tangent vector field, these are the coefficient functions, these are the basis vectors, then you get two terms. The covariant derivative is acting on the coefficient function, the covariant derivative is acting on the basis vectors. This is just an ordinary derivative. I mean, the covariant derivative acting on a scalar function just gives you the ordinary derivative. By the Leibniz rule, you also get a term where this is acting on that, and that gives us the Christoffel symbols. So you get ordinary derivative acting on the coefficient function, and then here you have the Christoffel, the term with the Christoffel symbols. This is again very similar to the covariant derivative that we had earlier. Ordinary derivative plus A field or B field. Here we have ordinary derivative plus Christoffel symbol. Or really connection 1 form. And that, of course, encodes gravity. But is this really also the generator of local Lorentz transformations, of infinitesimal local Lorentz transformations? And it is. So all we have to show for that is that these guys are generating infinitesimal Lorentz transformations. Okay, remember, the connection 1 form are not tensorial. Where do they take their values? They take their values in the infinitesimal Lorentz transformations. And why is that? Here's an intuition for it. The intuition is that, oh my God, high time for a break. The intuition for that is that the affine connection gives us infinitesimal parallel transport. Okay, it's the differentiation with respect to infinitesimal parallel transport. How much does a vector change as the infinitesimally parallel transported? Well, and under parallel transport, vectors can change their direction, but they cannot change length. In other words, the metric is, you know, the metric in between two vectors parallel transported stays the same, right? So under parallel transport, at most you can have a Lorentz transformation on a vector because it doesn't change its length. Therefore, the affine connection naturally gives the infinitesimal Lorentz transformations. Now that's the intuition, but we can also prove this, and that's quite easy. Lorentz transformations, if you remember, are all those maps which leave eta the same. If we write eta as the Kronecker delta plus something small, infinitesimal Lorentz transformations, right? So that whole thing is an infinitesimal Lorentz transformation here. Then plug that into this condition, get the square, terms of epsilon square vanish because it's infinitesimal. And then we obtain, if we multiply all those things out, we obtain this equation here. And that's the equation to be obeyed by infinitesimal Lorentz transformations. Whenever you have a matrix epsilon that obeys this equation, then it generates infinitesimal Lorentz transformations, or ILT. So infinitesimal Lorentz transformation which obey this. You see, if you pull the indices down using the eta, then you just have this, which is to say anti-symmetry in those two indices. So then the question is, are connection 1 forms infinitesimal Lorentz transformation valued? Well, for this, we have to check what happens when you pull both indices down and see if it is antisymmetric. And I leave you with the proof to figure out yourself. I think we all, I leave it to you to read that in your own time. If you get stuck somewhere, let me know and I'll explain it, but I think we really need a break now. Okay, let's take a break for about 10, 15 minutes.